All right, hey everybody. I wanted to go over the review for Thursday's quiz. We said Thursday, right? So let's start with number one. Here you're being asked to find each of the following in its domain. So when they say find each, they mean, write a rule to model the the function. So let's do that. When you see f composed with g, you remember, I'm sure, that means f of g of x, where g is the inner function. So I like to think of sort of taking the outer function f, and you go 1 over the square root of, and then instead of x, you just have this sort of empty shell. And into that empty shell, you need to plug all of function g, whatever it is. And so for us, that's this big, long, quadratic trinomial. 3 terms is a trinomial. So in goes the x squared minus 3x minus 4. That's a little small. You can read that, probably. Okay, so we did it. We wrote a rule. Can this be simplified? Let's find out. If I can factor, I'm supposed to factor. So let's definitely start by factoring this quadratic. 4, let's see, factors of 4 that add up to 3, what could they be? How about 4 and 1? So it'll be x minus 4, it'll be x plus 1. That's my factored form, but both of those things still go under a radical. So that's the best we can do. That's our sort of fun. Well, I shouldn't say this is the best we can do, because of course, back in the day, we would clean up radicals in our denominator. But that's not anything we have to do anymore, so we can technically stop. So now, more importantly, they want us to find the domain. And I could build my domain just off of this function, and honestly I probably should, but sometimes when you find your domain just by looking at the algebraic rule that results from the composition, you can lose exclusions from your domain. You can miss something that needs to be excluded if all you do is look at this. So let's maybe try to, reverse engineer the thing. Let's start by looking at the domain of G like we're supposed to. And luckily, since the domain of G is all real numbers anyway, that's a pretty easy hurdle to jump. We know there's nothing that can't be plugged into G. But now we have to worry about, well, okay, are there any values of x that are in the domain of G, but that map onto y values that are not in the domain of f? So looking at function f, I think it's pretty clear that as a rational function, we can't divide by 0. So 0's out. But more than that, there's also a radical here. So we can't take the square root of anything negative, or else we'll be imaginary, or really, we should say, non-real. So I think the best way to attack this would be, and I've been harping on this in class, but think about this graphically. Take this quadratic, x squared minus 4x minus 4. And if you can't picture the graph of this, I could excuse you for that. But here's what you should be able to picture. You should be able to picture the graph from the factored form. The fact that in our factored form we equal x minus 4 and x plus 1 means that 4 is one of the zeros of this quadratic. So I can go over to 4, plot an x-intercept. Negative 1 is another zero of this quadratic. So at negative 1, I would get another x-intercept. The other thing you should know is because your leading coefficient is positive, you know that both of your end behaviors, well, am I having this discussion? I guess I am. If your leading coefficient is positive, then your right end behavior tends toward positive infinity. And if your degree is even, then your end behaviors are the same. And so obviously in the middle, we're doing one of those. I probably could have just said that for any quadratic with a positive leading coefficient, you know that we open up. But the deeper conversation to have here, and I think you should know all this from last year, is really around the end behaviors. If your leading coefficient of any polynomial, I don't care if it's quadratic, but any polynomial, when leading coefficient is positive, the right end behavior will tend towards infinity. When the degree is even, your end behaviors have to be the same. So if this was a cubic, then you would know one end is up, but the other end is down. Because when it's cubic, or odd, the end behaviors have to be different. But anyway, here's a super quick and dirty sketch of my quadratic. And guess what? If I don't want this quadratic stuff to be negative, then it seems like this interval of x values is bad, right? So call me crazy, but I can't help but think that the domain of f composed with g will not in fact be all real numbers. It'll actually only be the values of x that when plugged into g map onto positive values. And notice the zeros here are not good, because if we plug in 4, then we get out 0. Then we try to plug in 0, and the square root of 0 is fine. But then you get 1 divided by 0, which is not fine. That's undefined. So that would mean my interval, or my domain, would be the interval that starts from negative infinity, runs up to the negative 1, does not include the negative 1, and then I also get a second interval that starts at 4 but doesn't include 4 and runs to infinity. So there. So it does turn out that if we just based our answer to what the domain would be on this algebraic rule, we would have been fine. We would have known that, hey, I need to be between negative infinity and negative 1, I need to be greater than 4. We wouldn't have lost anything. But hopefully somewhere we'll see an example of a problem where if you base your answer just on the algebraic rule that you come up with, you're going to miss something. All right, let's do B. And let's do B after drawing a little line to divide this space. Yoink. And then I can move this over. Have a little more room. All right, so this is G composed with F. That means we're going to just compose our functions in the other order, which means we're now taking F and making that the inner function of the quadratic. So instead of x squared, we have empty space squared minus 3 times not x, but empty space minus 4. And into that empty space where the x's used to be, we're cramming all of function f of x, so the 1 over root x. Okay, so this will be a little bit ugly, but that's okay. To square this, when you square a fraction, you square the numerator and you square the denominator. So 1 squared is 1, and root x squared is x. Now what? Here I'm just multiplying by 3 over 1 essentially. So the 3 and the 1 will multiply to make a numerator of 3. The 1 times root x will give you just a root x in your denominator. Then you've got this minus 4 on the end. And I can't think of anything I would do to this algebraically to clean it up anymore. I don't think we're going to want to generate a common denominator and pull all these things together. Or do we want to do that? I'm sure we don't. Let's do it anyway though, because it wouldn't kill us to give an answer that was just one term. You know, kind of. So what would we do? This would have to get multiplied by root x over root x. So you get root x over x root x. This would get multiplied by x over x, giving 3x over x root x. And this, of course, would have to get multiplied by x root x over x root x. So you get 4x root x all over x root x. And you guys can see why I was really saying that we probably shouldn't do this. But at least now that we've done it, we could say the answer is root x minus 3 minus 4x root x all over x root x. So is that simpler now that it's expressed as sort of one big thing with one common denominator? No, I wouldn't say it is. So this green version up here, that's probably your best bet, is just to get this answer and leave it alone. Although it would be a good thing if you at least understood how to get from this green expression to this blue expression. Okay, so anyway, I'm now supposed to find my domain. So let's do this the lazy way, and let's base our answer off of this algebraic expression. Based off of this algebraic expression, I would say I can't divide by 0, so 0's out. I'd say I can't take the square root of anything negative, so anything less than 0 is out. And just as a lazy bones way of figuring this out, I would say the domain of G composed with F is just going to be 0 to infinity. Am I missing something? I'm probably not, but now let's take a less of a lazy bones approach, and let's actually work from the inside out. So who's in the domain of f? Well, it's 0 to infinity, but not including 0, because we can't be negative or else we'll be non-real. We can't be 0 or else we'll have division by 0 and we'll be undefined. So this does happen to actually be just the domain of f. Okay, then we have to worry about, hey, is there anybody in the domain of f that maps onto a y value that's not in the domain of g? And again, g has a domain of all reals. So that secondary hurdle of worrying about the outputs of f being valid inputs of function g, well, function g doesn't care. Function g will take any inputs anyway. So this is another one of those situations where from the domain of f we do not need any further restrictions, and we do just get that as our answer. So that's it. That's a couple of ways to think through the domain of that composition, and a couple of ways to think through the final algebraic expression for that composition. Hopefully that makes sense. All right, that took me 11 minutes to do 2 problems. Maybe I should pick up the pace, but I don't think I should. I like for these videos to be pretty comprehensive. Moving on. Hey, let's do h composed with g, which you will not pronounce as hog. This is h composed with g. All right, so this means h of g of x, which means if we're trying to write the algebraic rule to model this, then it's function g getting crammed inside of function h. Ooh, that's a bloody nightmare. Okay, well, do it anyway. So the x in our numerator becomes this entire quadratic trinomial. So x squared minus 3x minus 4. And then the x in the denominator also becomes x squared minus 3x minus 4. But then there's also a minus 6. So there it is. So let's clean this up. We know that in the numerator we can factor. We've already factored this thing. We do have to do it again. So it'll be x minus 4, x plus 1. In the denominator, these parentheses that I put in, they're not really doing anything. They were just placeholders to represent the fact that I had plugged in for this x. But those parentheses can literally just be gone. And then you combine like terms. The minus 4 take away 6 is negative 10. So in our denominator, we've got an x squared minus 3x minus 10, which may or may not be factorable. 5 and 2 feels promising. Yeah, I feel like that's gonna be factorable. So we're gonna get an x minus 4x plus 1 in the numerator. In the denominator, we're gonna get x minus the 5 and x plus 2. Parentheses on all of these. There you go. So that's it. What is ever so slightly unfortunate is the fact that none of these factors are sort of shared factors, common factors in the top and bottom that we could cancel out, because then we could have a conversation around that. Hey, I've got an idea. Why don't we have a conversation around that anyway? Let's just go down here for a minute, and let's imagine a world where we factored. Maybe we got something like an x squared minus 9 in the numerator. Let's pretend like downstairs we got something like x squared minus 10x, and I want a 3, 13, 3. If I'm trying to get the 10, 7, oh, I'm bad at this. I wish I didn't do this. All right, I gotta have a factor of 3 and a 10. 3 and 7, 21. But they gotta be different. 3 and 13, 39. Let me just make this a plus. 21. Yeah, I like that just fine. Okay, imagine a world where this is actually what you got. And then imagine that you totally remember how to factor the numerator, because that's a difference of squares. So wouldn't it just be an x plus 3, x minus 3? Those are easy. Then in the denominator, you totally recognize that 21 has factors of 3 and 7, and if you make them both negative, this will still come out positive, and the two negatives will have a sum that is negative. So you can go x plus 3. Ooh, super psych. What you can actually do is x minus 7 and x minus 3. Oh, would you look at what I did there? In this situation, if you've got a common factor, you can cancel those factors out. But do remember that thing I said in class, which is when you cancel that out, you have to tell somebody. You have to actually say, hey, this expression's all good and everything, and it's totally equivalent to this expression, except this expression here in blue, it's undefined when x is 3. I can see that it's undefined when x is 3, because I would get 9, take away 30, plus an extra 21. That would be 0. I would be undefined. But here, when I take that factor away, suddenly 3 as an input seems fine. 3 plus 3 gives 6. 3 take away 7 is negative 4. I'm getting negative 3 halves, which feels like a perfectly valid output, but we know that it's not. Based on the original definition of the function before I simplified, 3 was not a valid input, and you have lost that information by factoring and canceling and all that. So you must not lose that information. You have to actually stipulate after the function that x cannot be 3. And if you do not include that domain restriction here, then you haven't really given me an equivalent expression. You've given me an expression that is equivalent a lot. It's very often equivalent, but for the input of 3, the blue and the orange are not really the same. So make sure you include that, or else you'll be in big trouble. All right, there. I've had that conversation. Moving on. Yoink. All right, remember this? Here's this one. So I don't need to make any stipulations about my domain here, because everybody can still see that 5s are bad and negative 2s are bad. And I don't think we have any other restrictions. Even if I go back and think about inner function, outer function, g of x as my inner function has no restrictions. H of x says thou shalt not be 6, right? But guess what? If we didn't have this expression, then we'd be saying, okay, well, it's not 6 who's bad, because 6 gets funneled into function g first and turned into something else. If I plug in 6 squared will be what? 36. Take away 3 times 6 is 18. Take away 4, that's 18. Take away 4, that's 14. So 6 is in our domain. It might not be in the domain of h, but it's in the domain of h composed with g, because g takes the 6, turns it into a 14, then you plug in 14 into h and everything's hunky-dory. So who's the bad guy then? The bad guy is whoever g of x actually maps onto 6. So you got yourself a mini equation to solve. So I would subtract 6 from both sides. Set that equal to 0. I would factor this. And yes, this should be looking familiar. Plus 2. And of course I see that x equals 5 and negative 2 are actually the domain values that need to be cut from the domain of h composed with g. And oopsie daisy, would you look at that? The algebra that we did actually made that obvious for us already. The fact that 5 and negative 2 are bad, well, this is why. 5 is bad here because 5 plugs into g and yields 6, which plugs into h and causes us to be undefined. Negative 2 does the same thing. Plugging in negative 2 gets positive 4 plus 6, take away 4, which of course would be 10 take away 4, which is 6. It's bad. So we're actually fine. So all this math here, for this particular problem at least, it's not really necessary because our algebraic rule is showing us the 2 domain restrictions that we need to worry about. They're right there in the denominator. So there. For more complicated problems, we might have to think a little more deeply, but for this problem, those 2 domain restrictions are all we need. So let me just write that down then. The domain of h composed with g is all real numbers except for negative 2 and 5. And as I mentioned before, when you're listing the elements of a set, they are technically supposed to go in numerical order. So do that. Okay, next one. line. All right, f over h. This is probably going to be a pretty straightforward one. For these quotient functions, you tend to just have to put the numerator in the numerator, denominator in the denominator. Often there isn't much you have to do. The only time you do have to do some extra junk is when one of your functions is already a fraction, and then you end up with a fraction inside of a fraction, which of course is the case. We have 1 over root x in the numerator, and then h is another one, so we get x over x minus 6. So this is like worst case scenario where we have a complex fraction. But I still say that the best way to think about this is to think about this middle fraction bar here, this big boy. Just think about that as a division sign. And just think of this as a 1 over root x divided by x over x minus 6. And then remember that the way you've always dealt with division of two fractions is to keep the first fraction, leave it alone, and just, instead of dividing by this fraction, multiply by its reciprocal instead. And that's going to land you on a final expression of, let's see, 1 times x minus 6. If this was anything other than 1, I'd be all worried about you guys remembering to distribute it onto both terms. So just remember, if this was a 2, this makes 2x minus 12, not 2x minus 6. Since it's a 1, we don't have anything to worry about. We get x minus 6 in the numerator, we get x root x in the denominator, and then we just throw a box around it. Because that's the best we can do, unless you guys want to go back in time to a land where radicals were not allowed in the denominator, and then if you really wanted to do that, you could multiply by the root x over root x. Remembering that, of course, you now need parentheses around your binomial so that this would actually distribute onto both. But then I would say, don't distribute it onto both. Just leave that in factored form. X minus 6 root x. In the denominator, you'd have x times x. Your denominator would be an x squared. So this would be your expression if you did have to rationalize your denominator. But this orange stuff is fine if you just left it as x minus 6 over x root x. Okay, so maybe more importantly, what's our domain? Well, again, let's see if we get into trouble just basing our answer off of this algebraic rule. Based off of this algebraic rule, I can see that 0 is not going to be allowed because it would cause us to divide by 0. Based on the radical here in the numerator, I know that I can't have any negative values. So if I can't be negative, then I guess I have to be greater than 0. The radical says 0 is fine, but then the denominator says no, 0 is not fine because that'll be division by 0. So hard bracket made soft seems to be saying that the domain of f over h will just be 0 to infinity. And that should be correct. Remember, when you have a quotient, you do the intersection of the two domains, with the domain of f, well, is literally this. 0 to infinity, but no zeros. And the domain of h is, of course, all reals except for 6. So guess what? This is not fine. Haha. And that's good, because it's important that you guys recognize that you can't base your answer for the domain just off the algebraic rule that you find here. Okay? If our domain has to be the intersection of the two domains, then if 6 is not in the domain of h, then I don't care what happened algebraically from here to here. 6 is not in our domain. You have to cut it out. So that would mean that our domain had better actually be 0 up to 6, close parentheses, union 6 to infinity. And oh, guess what? That means we have the pleasure of going back here and actually stipulating that, oh yeah, this is not quite right. X is not allowed to be 6. You'd have to go back and kind of build that into your statement of the algebraic rule. You'd say, hey, this function is great as long as you don't let x be 6. Now, hope that idea is making sense. Let's throw a box around this. That's our lovely domain. This, again, this light blue answer, That's the answer only for people that want to go above and beyond. This orange answer we said was fine. This answer of just x minus 6 over x root x. But even here, you'd have to stipulate that x can't be 6. All right, I hope I'm not making too much of a mess of this. Moving on. Wait, hog? We already had hog. Oh no. All right, let me hit pause and figure out where I went wrong.